we're going to cover integration. Let's start off with basic power rule integration. We have the integral of x to the power of n times dx is equal to x to the power of n plus 1 divided by n plus 1 plus constant c, where n cannot equal to -1. So in this concept, we have to add 1 to the exponent and divide by the new exponent. And we are going to rewrite radicals and fractions as exponents. We're going to use the power rule and add c. Let's say we have the integral of 4x to the power of 5 minus 3x squared plus 7 times dx. So here we have 4x. We're going to take our exponent and then add 1 to it. So that's 6 now. And then in the denominator, we're going to divide by the exponent plus 1. That's going to be 6 minus 3 times x. And then we're going to take the exponent, add 1. That's 3. Divide that by the exponent plus 1, which is 3. And then we have 7x because we're just going to take this as, this is a 7, right? So you have to add a 7x to it. When you're integrating it, it's the reverse of taking the derivative of it. And then you're going to add a constant c. So you can just simplify that fraction to 2 over 3, x to the power of 6 minus 7, or minus x to the power of 3 plus 7x plus c. Now, what if you have a negative exponent integration? That's if you have a integral of x to the power of n times dx is equal to x to the power of n plus 1 divided by n plus 1 plus c. You still use this formula, and for negative exponents, you're still going to use the power rule unless the exponent is -1. So you're going to rewrite fractions as negative powers. You're going to add 1 to the exponent still, and then divide by the new exponent. For example, let's say that we have the integral of 6 divided by x to the power of 4 minus 5 divided by x squared dx. So you can rewrite this using negative exponents instead, because we have this division of exponents in the denominator, and we don't want that when we are using integration, right? So we have 6x to the power of -4 minus 5x to the power of -2 times dx. So this is the same thing as 6 times x to the power of -3 divided by -3. So basically you are going to take this part and you're going to use this formula on this, right? So we have this x to the power of n plus 1, and you're going to use that on these parts right here. So you're going to add 1, and then 1 plus -4 is -3, and then -4 plus 1 is -3. So then you have -3 division right there. And you're going to do -5 times, do the same thing for this one. So we have x to the power of -1. We just added 1 to -2. And then we have division by -1. And then we're going to add c at the very end. And there's the plus c. You can just add that plus c at the end because it's always going to be plus c, and that includes all of the constants, okay? So this would be -2x to the power of -3 plus 5x to the power of -1 plus c. And if you want, you can rewrite this using these division of exponents, right? So you could do -2 over x to the power of 3 plus 5 over x plus c. Now, what about the special natural log x case? This is when we have the integral of 1 over x. Whenever you have the integral of 1 over x times dx, you just rewrite the whole entire thing using the natural log of the absolute value of x plus c. And always remember that if you have the absolute value of a something squared, right, you know x squared is always going to be a positive value. So then you don't need to write the absolute value signs anymore. You can just write parentheses instead. So what you're going to do is you're going to look for 1 over x. You want to find this or something equivalent to this. You're going to use the natural log and then absolute value here. Let's say you have the integral of 3 over x plus 4x squared times dx. So you see that you have this 1 over x, right? Therefore, we can use that formula. Now we write this with 3. You can move this 3 out, right? So we have 3 natural log of x, and then we still have 4. And then we have the power rule over here. We have x n plus 1 divided by n plus 1. So you're going to take this 4x squared you have here. This x squared, you can write that as x cubed, because 2 plus 1 is going to be 3. And then you have divided by 3. So you still have 4 out here. And then this is going to be plus c, because you have to remember to add your constant c. So that is going to be your final answer. Now, what if you have radical integration? This is going to require you to take the exponent rule of when you have something to the root of this, right? Root of n, right? X to the power of m. This is the same thing as taking x to the power of m, the thing that you raised it to the power of, that's going to be the power of the thing that was inside of here. So your m right here, and then you're going to divide it by the thing that your root was of. So that's m over n. So you have the integral of x to the power of n times dx. This is going to be x to the power of n plus 1. And you're going to divide that by n plus 1 plus c. Now you're going to convert your radicals into fractional exponents before you do anything. Now, then you're going to use the power rule, and then you can simplify if you need to. So you have the integral, for example, of 5 root of x minus 6 divided by the root of 3x times dx. You can rewrite this with your fractional exponents. So we have 5 to the power of x 1/2. You can always remember this as the golden rule for yourself, as a reference for how you write that fractional exponent, because the root of x is going to be the power of 1/2. So then we have negative 6 times x to the power of negative 1 to the power negative 1 over 3. Because this is going to be a negative exponent since it was in the denominator. This is going to be all times dx. Now we can rewrite this using the power rule on each of these parts where we have something raised to an exponent. This will be rewritten as 10 over, and then 10 times x, and then we have 3 over 2, because we have 1/2, right? 1/2 plus 1 needs to equal to something. So you have 1/2, you can rewrite 1 as just 2 over 2, right? So you have 1 plus 2 is equal to 3. You have 3 over 2. So then you can divide this by 3 over 2, right? And you have that in your denominator. So this is actually 5. Then we have minus 6 times x to the power of, you have negative 1 over 3, and you add 1 to it, right? So then you're going to negative 1 over 3. You can write that as 3 over 3. So negative 1 plus 3 is going to give you 2 over 3. So now you can write negative 6 times x to the power of 2 over 3. Divide all of that by 2 over 3. And then you can add your constant c. So when you have division by a fraction, right, you can move that into the numerator. You can multiply by the reciprocal instead. So now you have 10, which is going to be 5 times 2, right? You're going to have 5 times 2, and then here you're going to have 6 times 3. So then that's going to be 10 in the numerator. You're going to have x to the power of 3 over 2 minus 9, right? Because 6 times 3, but you're going to have 6 times 3, and you're going to have to divide that by 2. So you have 6 times 3 is equal to 18, and then 18 is going to still be divided by 2 because the 2 is going to be in the denominator. You're going to have divided by 2 is going to give you 9. So that's how you're going to get 9 here. You're going to still have x to the power of 2 over 3, and you're going to add c. So this is going to be your answer. And also you have a division by 3 over here. This is going to be your final answer for this question. Now we're going to do some basic trig integration. There's some formulas that you have to memorize. Like, there is no other way you're going to get through BC without memorizing these. You have the integral of sine x times dx, and this is going to be negative cosine x plus c. You're going to have the integral of cosine of x dx is equal to sine x plus c. You have the integral of secant squared x dx, and this is equal to tangent x plus c. Okay, and then we have the integral of cosecant squared x dx. So look, these are each of these different trig functions, right, so far. Then we have negative cotangent x plus c. We also have secant x tan x dx is equal to secant x plus c. And then we have finally cosecant x cotangent x dx is equal to negative cosecant squared x plus c. So let's try to find some patterns here. Here we can see that we have sine x here, and then we have cosine x. So it becomes the opposite, and then we have a negative. We have a negative here now. And then we always have plus c, so you don't have to really memorize that pattern. You just know that it's always going to be a plus c at the end, right? Because you're taking the integral, you always have a plus c. And we can see we have cosine x in this case, and then we have sine x, but this time we have a positive sine x, no negative. So when you go from sine to cosine, it's going to be negated, but when you go from cosine to sine, it's going to stay positive. So for secant squared x, how can we remember this? So you can try to think of the Pythagorean identity, right? Because Pythagorean identity has secant and tan, and you can also think of the Pythagorean identity for this one. So these ones can be memorized using those strategies. And then same thing here. We can see when you go from secant squared to tan x, we have one of the cases where it's going to be positive when you go to the other form, and then one of them is going to be negative. So this one, the cosecant squared x to cotangent squared x, is going to be the one that is our negative case. And we can remember that because we can remember that these are both going to be c, so they're both going to be, one of them is going to be negative when we go taking the integral of it, right? So then, yeah, you can remember this one with secant squared x is going to go to tan x, and then we have cosecant squared x is going to go to cotangent x. So now we're going to have secant squared x times tan x. Tan x is going to equal to secant x. So this one you can memorize by using secant x is going to stay secant x, and then we're just going to get rid of the tan x, and then we have the plus c. And then for this one, same thing, we're going to get rid of the cotangent x. We have cosecant x here, and then this is going to be cosecant x. And here you have a negative sign. So when you go from the negative form, you have that negative sign. So we can remember we have a c here, we have a c here. And when you go to the negative form, right, you have the negative sign, right? And we can always remember that's for c, right? For c, you have that negative sign, right? Okay, so now let's actually do an example with these. Remember that these are just going to be the reverse of your derivative. Reverse derivative. So let's say, for example, we have the integral of 3 times cosine x minus 4 times secant squared of x plus 2 times cosecant x cotangent x dx. Well, first off, we know that cosine x, according to our list, we have the integral of that is just going to be sine x. So then we still have 3, and instead of cosine x, we can just write our sine x. We have just sine x minus, and then for 4, let's look at back to our rule, right? We have for secant x, secant squared x, when we substitute that in, we have tan x plus c. So that's going to be 4 times tangent x, and there's going to be no more square. So for this one, we get rid of the square afterward. This one, we get rid of the square afterwards. That's just going to be tan x. Now we have green. Now for 2 cosecant x, cotangent x, great. That's just the one right here, right? This is going to be our 6th case. So for all of this, we are going to get rid of our cotangent x, and then we're going to have, because it's c, right? We have a negative instead. We now have a negative cosecant x. So we can write this plus 2 times, and not plus 2. That is going to be negative, remember. That's going to be negative 2 cosecant x plus c. Now let's do some basic exponentiation integration. If you have an exponent, this is going to be our 6th case. We have the integral of e to the power of x times dx is equal to e to the power of x plus c. So the rule you're going to use is you have a to the power of x dx is equal to a to the power of x divided by the natural log of a plus c. So you need to know that e to the power of x is going to integrate itself. Now, basically, this represents your other exponential bases. Other exponential bases need to have division by natural log of a. Now, what we'll do for these problems is you need to identify if you have base e, which means you're going to use this case, or if you have another constant base. This is for another constant exponential base. You're always going to add c. Remember, still, you're adding c because we're integrating. Let's say, for example, we have the integral of 4e to the power of x plus 3 times 2 to the power of x times dx. So this is the same thing as 4 times e to the power of x plus 3 times 2 to the power of x over the natural log of 2 plus c. Now remember again, we see here for e to the power of x is a really easy rule. All you're doing is you still have e to the power of x, except you're just going to be adding c. There's no difference. And then for a to the power of x, when you have another constant value, all you're going to do is you still have a to the power of x. There's nothing crazy. You just divide by natural log of a. That's the only difference. So here, first case, we had e to the power of x, that's just stated. And then for this case, we had 2 to the power of x, and that's a constant, right? So then you just have to divide by the natural log, and then you have to put your argument as your number. See, you have still a here. Now, that is going to be your answer, except, yeah, we can just leave it like this. So now let's do some basic u substitution. Case 7, this is going to be our u sub. When we have u sub, we have this grand formula where it's not that bad. It's going to be f, and then we have the input of g of x. So then we have g prime of x is going to be multiplied by dx. So then this is going to be the same thing as f, the integral of f, input of u times du. So basically, you use u sub when you see an inside function and then its derivative inside. So we have an inside function, and then we have the derivative of the inside function. Our first step is we're going to let u equal to the inside function, and then we're going to find du. Then we're going to replace everything in terms of u, and then we're going to integrate and then substitute back our value of u. So let's say, for example, we have the integral of 6x times 3x squared plus 1 to the power of 5 times dx. We're going to see that our inside function is u. So we're going to say u is equal to 3x squared plus 1. And then we're going to take the derivative of u, which is equal to 6x, because you're going to take your 2, you're going to move this to the front, right? We're going to have 2 times 3, and then we're going to take 2 and subtract 1 from it, and then 2 minus 1 is going to be 1. So we have x to the power of 1, and we're going to divide by 1, but that's going to be the same thing as just what it is. So we can just leave it like that. And then we have the derivative of a constant, and the derivative of a constant is always equal to 0. So we just have plus 0. And then we have to write dx after it, because we still have, whenever we do that, we have to write dx. So now we can take what we have in our integral. We can see if we have these things, and if we don't have these things, we would do something else to manipulate it so that we have that exact thing. So we could substitute in terms of u. But in this case, it's perfect. We can just do straight substitution. So we see u was equal to this, and then we have 6x dx is right here. So then we can rewrite this in terms of the in terms of u, right? So now we have u to the power of 5 times du. This is the same thing as u to the power of 6 divided by 6 plus c. So you can substitute back our value for u. U was equal to 3x squared plus 1, right? So this becomes 3x squared plus 1 to the power of 6 divided by 6 plus c. Now let's do u substitution with adjustment. This is going to be u sub case 8 with adjustment. This means we still use the integral of f times the inside function g of x times g prime of x times dx. So basically, if our derivative is off by a constant, we want to multiply or divide to fix it. So we're still going to choose our inside to be equal to u. We're going to find the derivative of u du. We're going to adjust our constants, and then we're going to integrate. So in this example, we have the integral of x times x squared plus 7 to the power of 4 times dx. So we're going to make our inside function equal to u. That's going to be x to the power of 2 plus 7. And we have the derivative of this is going to be, we're going to move 2 to the front. So we're going to have 2x, and we're going to subtract 1 from 2, which is going to give us 1. And then we're going to multiply that by dx. So now we have to see that in our function, we don't, inside of this function up here, we don't have a 2x dx anywhere, but we do have an x dx. So we're going to make our goal to be finding x dx, and then we can do that by just dividing both sides by 2 here and dividing this side by 2. So now you have x dx is equal to du over 2, aka 1/2 du if you want. So now we can see clearly we have everything inside of our original function, and we can just substitute back in. Now we have x here and dx. So now in our new integral, we can move 1/2 to the outside because that's just going to be a scalar. And then we have the integral of u to the power 4 times du. So this is equal to 1/2 times u to the power 5 over 5 plus c. So this is the same thing as, let's multiply. In the denominator, we have 1 over 10 times u to the power, or we can just write u to the power 5 plus c. So let's substitute in our value for u. We said u was equal to u to the power of 2 plus 7, so we can write that right here. We have x squared plus 7, and then this is all going to be raised to the power of 5, all divided by 10, and then adding c as our constant. Now let's do an example where we have u substitution, u sub with natural log result. This is going to be our 9th case that you could possibly see on the exam. So we have the integral of u prime u dx is equal to the natural log of the absolute value of u plus c. So basically, if the numerator is going to be the derivative of the denominator, then that is how we know that the answer is going to be the natural log with absolute value signs. First, we're going to make u equal to what the denominator is, or what is on the inside. And then we're going to check that the numerator matches as the derivative of the denominator. And then we're going to take the natural log of u. So let's say, for example, we have the integral of 2x plus 3 divided by x squared plus 3x minus 4, all dx. And then we're going to see that in the denominator, we have this for u. So we're going to say that u is equal to x squared plus 3x minus 4, because that is our denominator, right? So let's take the derivative of this, and then we can see conveniently that's going to be 2x, moving that to the front, and then 2 minus 1 is just 1. And then dividing that by 1, it's just 1, so we can just write that if we wanted to. Here we have 3x, and then x to the power of 1 is just going to be what we have. We have 1 minus 1. You have 1 minus 1, right? So then 1 minus 1 is equal to 0. And then anything raised to the power of 0 is going to be equal to 1. So then we have 3 times 1, which just gives us 3. And then for negative 4, we are going to, that's going to go, the derivative of any constant is just going to go to 0, right? So then now we have all of this times dx. So where do we have 2x plus 3 dx inside of our fraction? We have that perfectly right here. So we can say that u is equal to this, right? And then 2x plus 3 dx is equal to our numerator. So that's so perfect. Now we can write our new integral as 1 over u dx. And if you remember earlier, when you have 1 over x times dx, or 1 over variable, whatever you choose to be your variable for substitution, right? This is equal to the natural log of u plus c. So that's basically the reason why we can use this u sub with natural log result, basically, right? So then we know that natural log of u, we know that u was equal to what we just wrote over here, right? So now we're going to write x squared plus 3x minus 4 plus c. Easy. Now let's do some u substitution, u sub with trig. This is our 10th case you could possibly see on the AP. So you have the integral of cosine of u, and then you multiply it by u prime, right? Dx is equal to sine u plus c. And we also have the case where sine of u times u prime dx is equal to negative cosine u plus c. So this was what we saw earlier with our trig, right? So when we go from sine to cosine, we have a negative sign that appears. And when we have our cosine and we go to sine, we stay positive. But look, in this case, we also have a u prime, and then here we have a u prime. So let's do some examples. The trig function is going to hide our chain rule in reverse. So basically what we're going to do is we're going to say u is equal to the trig angle, and then we're going to replace u prime times dx. We're going to integrate the trig normally, and then we're going to substitute back. So let's say, for example, we have the integral of 4x times cosine times 2x to the power of 2 plus 1 times dx. You're going to make u equal to your inside. We're going to make this equal to 2x squared plus 1, and we're going to make du equal to the derivative. So we have, bring down that 2, we have 4x, and then 2 minus 1 is just 1 times dx. So then we can substitute these back. We have this as u, and then we have 4x cosine x dx as du. So our integral is going to be equal to, what do we have left, right? We have cosine of x. So we have cosine here. So when we have cosine, that means that, let's actually use some different colors here for u, and since we have our trig functions, let's make du equal to this, and then u equal to that, and then du equal to this. So this is also a part of du. So because we have our cosine here, cosine, make it this color. So we have, in our new integral, we're going to have the integral of cosine, or sine u plus c. As a result, we could rewrite that as the integral of cosine u times du. So that's your input angle. So when you have the derivative of cosine, right, we know that's going to be sine, and that's going to stay positive, sine u plus c. So then for sine, we know, or for sine, we have an input of u. So u was equal to 2x squared plus 1. So you can just write that here. We have, for our final answer, sine times the input angle of 2x squared plus 1, and then we're going to add c to it. So let's do a case 11 where we have u sub with e to the power of u, which basically means we see something that we want to make u that is in the exponent of e. So we have the integral of e to the power of u times u prime times dx, and this will be equal to e to the power of u plus c. So basically, we just get rid of the u prime in the end. That's going to be our pattern, because we know that e to the power of u is going to be equal to e to the power of u prime. So what integration does is integration is going to reverse e to the power of u, which is equal to e to the power of u times u prime. Now, basically, we're going to make u equal to the exponent. Then we're going to check for u prime right here. Then we're going to integrate e to the power of u, and then we're going to substitute u back into our final answer. So that sounds like it's a lot, but it's actually really easy. We have 10 times x to the power, x times e to the power of 5 times x squared minus 1 times dx. So you're going to let u equal to your exponent, and your u is going to equal to the 5x squared minus 1, and then you're going to have derivative of u is equal to 10x times dx. So basically, let's see where we can put this back in. We'll make u equal to this, and then du is equal to all of this 10x and dx, and we're not including the base. We're going to have our base e. We didn't have anything to substitute that with, so we're still going to have that in our integral that we update with, right? So actually, yeah, so we have the integral of e to the power of u is still left over, and then we have times du. So if we take the integral of this is going to be e to the power of u using our exponent rule, and then we're going to add c. So then we just add what was u? U was just our value right there. So we're going to write e to the power of 5x squared minus 1, and then add c. So what if you have u substitution with a definite integral? Basically, in your 12th case, this means you have the integral of a to b times 5 times g of x, g prime of x times dx. Basically, for the definite integrals, you either have to change your bounds or you have to substitute back. So you're going to make u equal to what is on your inside, and then you're going to find du, and then you're going to change your bounds. You're going to take a and b, right? You can change them with your updated u is equal to g of x, right? And then you're going to integrate with your new bounds. So for example, let's say that we have the integral of 0 to 2 for the function 2x times x squared plus 1 to the power of 3 times dx. So basically, if you substituted in 0 and 2 into this, it's a really sloppy mess. If you'd have to do this on MCQ, it's just really long. So basically, you're just going to say that u is equal to x squared plus 1, and then du is equal to 2x dx. So then let's change our bounds. If we change the bounds, we get that when x is equal to 0, we have u is equal to, plug in 0, we have 0 squared plus 1 for our x, right? And then we have this will equal to 1. And then when x is equal to 2, we get u is equal to 2 squared plus 1 is equal to 5. And we're basically using the equation for u we have right here. We're getting this in terms of u. So that means that you have to take the equation for u and then just substitute in x instead, so we can get rid of those values for x. So then we can rewrite our integral using these new bounds. We essentially have that 1 is going to be our lower bound. 1 is less than 5, obviously. So we have u to the power of 3, and then multiply that by du. So again, let's look back here. We have u is equal to this stuff, and then 2x dx is out here. Let me write that clearer. So then this is how we get our new integral. Now all we have to do is just take the definite integral of this. How do we take the definite integral? Basically, you have to take 3, and then instead of subtracting like we did when we're going to take 3 and then we're going to add 1. So we have u to the power of 4 divided by 4. So we're going to take 3 and then add 1 to it, and then we're going to divide it by that number. So we're dividing u by 4. So then we take this and we evaluate it from 1 to 5. So basically we have 1, right? Or we have 5, right? So we're going to do 5 first. This is going to be your first number, and then this one's going to be the second one you have. So you have 5 to the power of 4. You just put 5 for 4, right? And then we divide that by 4. And then we're going to subtract 1 to the power of 4 and divide that by 4. So then 5 to the power of 4 is 625 minus 1 to the power of 4 is just 1. So then we have 4. And then from this, we get 156. So your answer is 156. So changing the bounds is going to let you finish entirely in terms of u, making you evaluate it way faster. Now, we're going to do our case 13, which is when we have integration by parts. Basically, we have the integral of u times dv is equal to uv minus the integral of v times dv. Basically, this is when you have a product, and this is when you have a product, right? So we have a product here, and also we have to have eliminated u sub as not a possible way to finish. So basically, how are you going to pick u? You have to pick u, and you have to use this trick, Liate. So L is going to be for your log, I is for your inverse trig, A is for algebraic, and T for trig, E for exponential. So then we're going to find what du is. Then we have to find what du is, right? And then we have to set the rest to dv. So set the rest to dv, and then we have to integrate and find what v is. So let's do an example. It's not that bad. We have the integral of x times e to the power of x times dx. First off, we have to pick u. We're going to make, one of our rules is we can make u using an exponential. Great, we have an exponential right there. So we're going to make u equal to x. So then we have to define the derivative of that. So that's just going to be du dx, because this is going to be x, that's just a constant, and then we're just going to have dx, we'll just multiply it by dx, because it's in terms of x, right? So then we're going to set dv equal to e to the x times dx, because we're going to set the rest equal to dv, right? So let's just write down what we have. U is equal to x, so then we get du is equal to dx, so then we're going to set x, let's make this color actually, x dx, or we have ex to the power of ex e to the power of x times dx equal to dx. We'll just set that equal to here. And then we have to find what v is. V is equal to e to the power of x. So if we apply our formula here, all we do is we just substitute all these values in. So we have x e to the power of x minus the integral of e to the power of x times dx, right? So then you have x times e to the power of x minus e to the power of x, because integral of e to the power of x is e to the power of x. And then we're going to add c to it. So then all you can do here is you see that you have e to the power of x here. You can factor out e to the power of x and then multiply it by x minus 1 plus c. So let's look back at our formula. You have u here. You put u out there. And you have your dv, right? You have your dv here. And you keep that in there. So we kept our e to the power of x in here, right? We kept e to the power of x right there. And we just continued on, right? So now let's do an integration by parts with the natural log of x. This is for case 14. So your formula is going to be u times dv is equal to uv minus the integral of v times dv. So for natural log of x dx, we need to know that natural log x dx, we're going to choose u is equal to the natural log of x, and we're going to choose dv equal to dx. So then we're going to apply the integration by parts, and then we're going to simplify. So let's say, for example, we have simply natural log of x times dx. So u is equal to the natural log of x, like we said, and then du is going to equal to 1 over x times dx, taking the derivative of that, because we know natural log of x is just, the derivative of that is going to be 1 over x, because this is just the reverse of integration, remember? So now for dv, we're going to make it equal to the dx. So let's just highlight what we've been doing so far. We have this for u, and then for du, we have, or for du, we get this, right? And then for dx, we're going to tackle that after. Or for dx, we're going to set that equal to dv, right? So then we just get that v is equal to x. So let's then write this using that x, natural log of x, minus the integral of x times 1 over x times dx is going to be what we have. So then you can cancel out that x here. So we have x, natural log of x, minus x plus c is equal to x, natural log of x plus c. Yeah, we can simplify that. It's just done. So let's do our 15th case, where we have integration by parts, repeated. So basically, we still have u times dv is equal to uv minus v du. So if you have a very high algebraic power, you may have to use integration by parts multiple times. So basically, you're going to choose your algebraic expression as u, and then you're going to, so u is going to be the algebraic part. And then you're going to choose dv to be equal to your exponential or your trig part. So then you're going to repeat this until you have no more polynomial, until it disappears. So we have the integral of x squared e to the power of x times dx. For the first round, we're going to say that u is equal to x squared. And then we have, from that we move the 2 down. So when we have 2x and multiply that by dx. So then for dv, we can set this equal to e to the power of x times dx. So then we get that v is equal to e to the power of x, because the derivative of e to the power of x is still e to the power of x. So then substitute everything back into our example here, right? So this is going to become x squared, or this is going to become x squared times e to the power of x minus the integral of 2 times x e to the power of x times dx. So now we're going to do integration by parts on this new thing. So then in here, we can see that we have u is equal to x. So we can make du equal to dx. And then we can set dv equal to e to the power of x times dx. So then v is equal to e to the power of x, because the derivative is just going to be e to the power of x. So then for this part, we can rewrite this as a new integral. So this is going to become x times e to the power of x, and then subtract the integral of e to the power of x times dx. And then that as an integral is, let's take the integral of this part right here. We can just know that simply e to the power of x. So we have x e to the power of x. So then now we just have to rewrite our entire expression. So 2e to the power of x is just going to be that. So in total, we can write x squared e to the power of x, which we have over here. And then we're going to subtract the 2 because we have multiplied by 2, right? We have to take out the 2. And we have x times e to the power of x. And we have to add that to 2 to the power, e to the power of x plus c. And we have all this. We can actually move the plus c out here. So this is going to come e to the power of x times x squared minus 2x plus 2 plus c. So every time you do an integration by parts, this is going to lowers the power by x. So let's do an example where we have trig powers and you have the odd power of sine. So this is for your case 16. For 16th case, you have sine squared of x is equal to 1 minus cosine squared of x. So basically, you have to know that if your sine has an odd power, then you're going to save one of the sine of x's, and then you're going to convert the rest using this part here, using the sine x is equal to 1 minus cosine squared of x, your Pythagorean identity. And then you're going to use that u is equal to cosine of x. So basically, you save 1 sine x dx, then you're going to convert the rest of the sine powers, then you're going to let us use that u is equal to cosine x, and then we're going to integrate. So let's do an example of this. So we have the integral of sine to the power of 3 times cosine to the power of 2 times dx. So basically, we're going to have that our sine to the power of 3x is going to be equal to sine squared times sine x. So let's rewrite this all as sine squared x times cosine squared x times sine x dx. So we can see that we have a Pythagorean identity here. This is our Pythagorean identity, where sine squared x is equal to 1 minus cosine squared x. So then we have the integral of 1 minus cosine squared x, and multiply that by cosine squared x times sine of x times dx. So then we can let u equal to what cosine of x is, right? So then we have that du is equal to negative sine of x, because that's when we take the derivative of cosine of x, it's going to be negative sine of x. So then we have that negative is going to be on the outside because we can factor out the negative, right? Because that's just going to be a scalar. And then we have 1 minus, where is every place in this equation where we have a cosine of x? We have one right here, we have one right here. So then this is going to become 1 minus u squared times times u to the power of 2, right? Times du, and sine of x dx. This was just equal to that, right? We also have a dx times here. I forgot to write that. So now we can write negative integral. We can distribute this u squared to each. We have u squared minus u to the power of 4 times du. And then we're just going to use our power rule, right? we still have negative on the outside, and we're going to use the power rule on each of these separately. So then we move the 2, so no, we don't move the 2. You're going to have u to the power of 3, right? And then over 3. You're going to add 1 to each of those. 2 plus 1 is going to be 3. And then you're going to have u to the power of 5, because 4 plus 1 is equal to 5. Divide that by 5, and then you're going to add c. So you have negative u to the power of 3. You'd have to distribute the negative, right? And then you're going to divide that by 3. And then you have u to the power of 5 divided by 5 plus c. So then what was u equal to? Again, u is equal to cosine of x. So then you can just write your cosine of x for each of those locations. You have this is equal to negative cosine to the power of 3 times x divided by 3 plus cosine to the power of 5 times x divided by 5 plus c. So that is going to be your final answer. Now, what if you have your trig powers with trig powers, and this time you are dealing with your odd powers of cosine? So this is not that bad either. You have, this is your case 17. You have to know your Pythagorean identity, right? Again, you have sine squared of x plus cosine squared of x, right? This is equal to 1 because that's your x squared plus y squared is equal to 1, equation of a circle. Basically, you can rewrite this, and we have cosine squared of x. We can just subtract this sine squared of x to the other side. So you're going to have 1 minus sine squared of x. So basically, if you have cosine of x has an odd power, right? You're going to save 1 cosine x dx, and then you're going to convert the remaining cosine powers with the cosine x, 1 minus sine of x. You're going to convert these all. Let's write this here. Let's write this in better, yeah. So you're saving 1 cosine x dx. You're going to use your Pythagorean identity and you're going to convert the rest of your cosine powers, and then we're going to let u equal to sine x. And then we're just going to integrate like we do normally, like we have been doing. So let's say, for example, we have the integral of sine to the power of 4. So sine is an even power, right? But for cosine, we're looking out when we have odd powers, right? We only care about when we have odd powers, okay? So we have cosine to the power of 3 times x dx. So cosine to the power of 3, we can rewrite that with our sum of exponents, right? So that's going to be cosine squared of x. Then we have cosine x. So then we can just rewrite the entire integral with sine. For x, we have cosine squared x and cosine x dx. So we're just going to let this part right here, this is awesome. This is our trig identity. Cosine squared of x is equal to 1 minus sine squared of x using the trig identity. So then just substitute in your entire thing with just this update, right? So let's take this, move this down here, and instead of cosine squared of x, we're just going to write 1 minus sine squared of x right here. And it's beautiful. Like, now we can say that u is equal to sine x, like we said we would make it. And then we're going to make du equal to cosine x dx. So if you have that, right, we're just going to say that we have the integral of u to the power of 4, right? Because sine of x is equal to u, right? And then we also have a sine x here. And we have a du cosine of x. So that's right there. Perfect. Everything works out. U to the power 4 minus 1 over u squared times du, because you have a square left over in there. And then you can write this by distributing the u to the power 4. So then you have the integral of u to the power 4 minus u to the power of 6 times du. Now we're going to use the rule right here, the power rule right here, on each of these individually. So we can now get rid of our thing now, because we're using the power rule. We have u to the power of 5 over 5 minus u to the power of 7 over 7 plus c. So this becomes sine 5 to the power of 5x over 5 minus sine to the power of 7x over 7 plus c. So if you save 1 cosine, that means you can write your du is equal to cosine x dx, right? That's exactly what we want. We're done. So let's do our 18th case. This is when we have our trig powers, and we have even powers of sine and cosine. So basically, you're going to have sine squared of x is equal to 1 minus cosine twice the input angle of x, and divide that by 2. You're also going to have cosine squared of x is equal to 1 plus cosine 2x all divided by 2. So if both cosine and sine are even, we're going to use our power reducing identities. So basically, we're going to replace sine x and also cosine squared x. Then we are going to expand, and then we're going to integrate the basic trig terms. It's not that bad. So we have, for example, the integral of sine squared x dx. Looks simple, but it's even, right? So we're going to have to do something about that. And we can write this knowing that sine squared of x is equal to this relationship right here. We know that. So we can just rewrite the integral using our 1 minus cosine squared x, cosine input angle of 2x actually, over 2 times dx. So you can move that. We have this 1/2, right? So we can move that to the outside, but we still have a division by 2, right? So we have 1/2 out here times 1 times dx. 1 times dx minus 1/2 times cosine x, or cosine 2x, I mean. So that's just us distributing that 1/2 to each of the terms on the inside, because we had a 1 on the inside, and we also had a cosine 2x on the inside. So basically what we can do next is just write that as x over 2 minus 1/2 times sine 2x over 2 plus c, and then you can just multiply those 2's. You get x over 2 minus sine 2x over 4 plus c. So this is when simple u sub does not work. Now, when we have tangent and secant powers for case 19, we have tangent squared of x is equal to secant squared of x minus 1. So we have that secant squared of x is equal to the derivative of tangent of x. So basically, if you have even powers of secant, you're going to save your secant x powers, secant squared of x dx powers, and you're going to convert your tangent x powers. So basically, first of all, we're going to save our secant squared of x dx, then we're going to convert remaining secant squared of x using the identity that secant squared of x is equal to 1 plus tangent squared of x using your Pythagorean identity, right? So then we just integrate after this. Let's do an example where we have the integral of tangent to the power of 3x secant squared of x times dx. So we're going to let that u is equal to tangent of x, and we're going to let du equal to secant squared of x times dx. So we're going to have the integral here, right? And then we're going to substitute in instead of u. We can write that as tangent of x right here. And then for secant squared of x, conveniently, we have that right there. So we can write all of this using u to the power of 3 times du. So then we can use our power rule on u to the power of 3, so we have u to the power of 4 over 4. Then we are going to add our plus c, so then we can substitute back in the value for u right here, and we get tangent of x is raised to the power of 4 times x, all divided by 4 plus c, right? So then now let's handle our case where we have secant and tangent with odd secant powers. So all we have to do in this case, pretty easy, we just have to memorize that d over dx times secant x is equal to secant x tangent of x. So if you have tangent squared of x, this is equal to secant squared of x minus 1. So basically, if you have secant x tan x as a factor, we are going to use u is equal to secant x. So basically, we're going to save secant x tan x dx. Secant x tan x, save secant x tan x dx. Then we're going to convert remaining tan remaining tangent x powers with the Pythagorean identity. So then you're going to let u equal to secant x, and then we're just going to integrate. So let's do an example of this. We have the integral of secant to the power of 3 x tangent x times dx. So then we're going to rewrite this. We have let's rewrite this a little neater, tan x dx. We have secant squared x. We'll rewrite tan x. We have secant x tan x dx. We can rewrite the power of 3, right, with this. So then we just have u equal to secant x, and then we're going to let du equal to the derivative of this. It's going to be secant x tan x. All we do is just bring in the presence of tan x. So then we can rewrite the whole integral using what we have. We have u for secant x right there, and then we have tan x dx for du. So we have u squared times du. So we can use the power rule on this. We have u to the power of 3 over 3, and then we're just adding plus c. So then substituting in the value for u, we have secant to the power of 3 over x divided by 3 plus c is going to be our answer. So not that bad. What about when we have partial fractions? This is our 21st case. We have partial fractions with distinct linear factors. Distinct linear factors. So basically, when you have your p over x, your function, divided by the factor form of another, we have x minus a over x minus b. This is equal to a. You make it equal to one of those, x minus a, and then the other one, b over x minus b. So we're going to use partial fractions for the rational functions when we have denominator factors. So we have our factors down here. The first thing we do is we have to factor the denominator, right? Then we're going to split into these fractions here. Then we're going to solve for the constants, and then we're going to integrate the logs. So let's say we have the integral of 5x plus 1 divided by x minus 1 times x plus 2 dx. So you're going to split this into a over x minus 1 plus b over x minus 2. So then all we're going to do is multiply by the denominator. You're going to take your denominator, 5x, or you're going to take your denominator, you're going to multiply this. Up here you have x minus 1, and then you have x plus 2. So then if we multiply to each of these, this is basically going to cancel out the x minus in, let's see here. So let me actually do a different color here. We have our x minus 1. That's going to cancel out one of those there, but we're still going to have an x minus 2 here. And then for our second one, we have an x minus 2. So the x minus 2 is going to cancel out here. This should actually be x plus 2. So that x plus 2 is going to cancel out here because 1 over 1 is just going to be equal to 1. But then we're still going to have an x minus 1 that is going to multiply here, and that's going to count. So then we are going to get on the other side, we still have our 5x plus 1, right? So we have our equation 5x plus 1 is equal to ax plus 2 plus b times x minus 1. So then we have to substitute in values for x, right? So let's say x is equal to 1. So we're going to get 5 times 1 plus 1 is equal to a times 3. Because if you have 1 in here, this part's going to cancel out. So you ignore the part with b. You ignore the part with b. And then when you have x is equal to negative 2, we plug in here negative 2. So then we have, ignoring the part with a, we just get 5 times negative 2 is equal, or plus 1, is equal to b times negative 3. So then you can just multiply 5 times negative 2. That's going to be negative 10 plus 1. This is going to be negative 9. And then we have negative 3b. So b is equal to 3. Now, what can we do? We can just rewrite the entire integral in terms of this. We now have the integral of these two fractions. We get 2 over x minus 1 because we know that a is equal to, okay, a over here is equal to 2, right? Because we have 3a. So we have 2 over here, and then we have plus 3 over x plus 2, and then we multiply all of this by dx. So then you can just write this when you have 1 over x. We have a 1 over x, and then we can just write that. We have a 1 over x, right? So then you can just write that using natural log. So whenever we have a 1 over x, remember, that's going to be the natural log of x. The integral of 1 over x is equal to the natural log of x plus c. So then you have 2 times the natural log. You have x minus 1 here because you just divide it by, or you have the natural log because you have the input, right? And then we have plus 3 because we said u was equal to, or u is just going to be our x minus 1 here. And then for x plus 2, we have that as the division of what was our natural log, right? So then we have 3 times the natural log of x plus 2 plus c. So what about the case when we have repeated linear factors? So all we have is p over x minus a, where this is a factor that has multiplicity, right? An x-intercept with multiplicity, so it bounces off. We have a over x minus a plus b over x minus a squared. So when you have repeated factors, you're going to need a term for each power, right? So we have one term for the first power, and then for the second term, we have for the second power, right? When we have it squared, the squared version, we're going to have to add another factor where we have b over that. So we are first going to factor our denominator, right? And then we're going to include each of our repeated powers. Then we're going to solve for the constants, and then we're going to integrate each term. So let's take, for example, the integral of 3x plus 5 divided by x minus 2 squared dx. So this part here, we can write that with partial fractions a over x minus 2. And then if we have our squared, right, that's going to be plus b over x minus 2 squared. So if we multiply this, we're going to have 3x plus 5 is equal to a times x minus 2 plus b. So then let's just distribute that. We have now ax minus 2a plus b. We have 3x plus 5. So basically here, all we did was multiply by our denominator on both sides. We have x minus 2 and then x minus 2. So now what we can do is we can match our coefficients. So we're going to say that a is equal to 3. So you match your coefficients. A is equal to 3. And then for our constant, or this is for linear, right? So basically you just take 3x is equal to ax, and you get a is equal to 3. And then for constant, you're going to take your constants here. You're going to say 5 is equal to negative 2a plus b. So you get negative 6 plus b is equal to 5. So then you get b is equal to 11. Now all you do is just rewrite. So this is pretty fine. We have the integral of 3 over x minus 2 plus 11 over x minus 2 squared dx. So we have 3 natural log of x minus 2 plus 11, the integral of x minus 2 negative 2 dx. So then this is 3 times the natural log of x minus 2 minus 11 times x minus 2 to the power of negative 1 plus c. So then we have 3 times the natural log of x minus 2 minus 11 over x minus 2 plus c. So basically our repeated factors, we always remember that you are going to need both x minus 2 and x minus 2 squared denominator terms. So now what if we have an improper rational function? What this means is, for case 23, we have the degree of the top is going to be greater than or equal to the degree of the bottom. So we're going to use polynomial division first before we do anything else. So this is thinking back to like pre-calc, right? So for example, we have the integral of x squared plus 3x plus 5 all over x plus 1 times dx. So if we divide with partial fraction, or no, before we do partial fraction decomposition, I mean, we have to divide this, right? So we have x squared plus 3x plus 5. So we have x plus 1. We have to ask ourselves, how many times can x plus 1 go into this? Let's do x plus 1 times something, right? We can do or we're going to get from the result of this, actually. Just write the results to save time. We have x plus 2, and we have 3x plus 1. So we have a remainder here, but we don't really care about that. We can just leave this here because we're not evaluating this rational function. We're just writing out what this integral is. So you have the integral of x plus 2 plus 3 over x plus 1 times dx. So then we have our x right here, right? So we can use our rule on this, our power rule on this. At least we have x squared over 2, and then we have for our 2, we have to add our x there, so we have 2x plus 3, and then we have the natural log of what's on the denominator, x plus 1, right, plus c, because this was a constant, so that's going to be your answer. Now for our 24th case, we have to complete the square, aka when we have arctan. So a formula for this is 1 over x squared plus a squared is, or times dx, this a squared dx, is equal to 1 over a tangent negative 1 x over a plus c. So basically, if you have quadratic denominators, they cannot factor. And if they can't factor, they're going to become arctan. So you may have to complete the square if needed, and then you're going to match your u squared plus a squared, and then we're going to use the arctan formula. So let's do an example of this. If you have the formula, it's pretty easy. So if you have 1 over x squared plus a, or 1 over x squared plus 4, times dx, we're going to say here x squared plus a squared, it's going to be x squared plus 2 squared, just to rewrite. So then we can rewrite this whole thing as 1/2, because now we can see what our a is, right? So we have 1/2, and then we have tangent negative 1, and then we have x over 2 plus c. So that's going to be your answer. Now let's do an inverse sine form for case 25. This means you have the integral of 1 over the root of a squared minus x squared dx is equal to sine negative 1 x over a plus c. So basically, if you have the root of this, you're going to produce inverse sine usually. So you're going to match your a squared minus x squared, and to take the root of all of that, you're going to match that. To find this, and you have to match it. And then you have to identify what your a is. This is your mystery, right? You need to find what a is, and then we're going to use this inverse sine formula. So basically, let's do a setup where we have this. We have 1 over 9 minus x squared times dx, and you can see here that a squared is equal to 9. So we have this as, a squared is equal to 9, so a is equal to 3. So your answer is just going to be sine negative 1 x over 3 plus c, because it matches our pattern. So how do we find the area under the curve? Area under the curve, this is the 26th case that we're going to have. If we have the graph is going to be above the x-axis, right? That means the area is going to be equal to the definite integral. Say that it's above the x-axis. So we're going to first identify what the interval is. We have to find what a to b is, and then we have to evaluate it. So let's find the area that's underneath the f of x is equal to x squared plus 1. So let's move up 1 here, and then we're going to have a parabola that is opening upward. Since it's above, we can find what the area is, and we're going to find this on the interval from x is equal to 0 to x is equal to 2. So we're going to say from 0 to 2. So this is going to be the lower bound, and then this is going to be the upper bound. So then our area is going to be equal to 0 on the bottom, and then you have your upper bound on the top. It makes sense because it's on the top, and then this one's literally on the bottom. So just think about that if you forget. And then you have x squared plus 1 times dx. So basically what you do is you're going to take your 2, and then you're going to add 1 to it. So you have x to the power of 3 over 3 plus x, and then you're going to put 0 on the bottom still, and then 2. So what you do is you're going to put this part first since it's on the top, and then this part is going to be evaluated second, and you're going to subtract this, or you're going to add this away. So because we're finding the area, you have to add, right? So we have x to the power, or what is it? We have 2 to the power of 3 over 3 plus what x is, right? And x is just 2. So then if we do 0, you're going to have 0 to the power of 3 over 3 plus 0. So this is all going to become 0. So this, it just ends up being 8 over 3 plus 6 over 3. Because for the 6 over 3, you can just write 2 as 6 over 3. So then we have 14 over 3 as our answer. So what if you have net and negative sign area? Net slash negative, or we want to find negative area, right? If you have negative area geometrically, that doesn't make sense. So we call this signed area in terms of the integral. So basically we have a to b, we have f of x dx is equal to the signed area. So basically the area above the x-axis is going to be positive area, and then this is going to be negative area. So all you do is integrate normally, you keep the signs, and then you don't make anything positive unless you're asked for the total area. So what if we have negative 1 to 1 x power of 3 dx? Well, you're just going to, because you are looking at the negative part of the graph too, it's going to be kind of undone. So if we have x to the power of 3, this is going to snake through the center. So it's going to be like this. So you have from negative 1 to 1, this is going to be the area from here. So this is going to be this part. We have like this literally undoes itself because we're going from here to here, right? And then if you have all that area, it's just gonna, let's just do this. We have x to the power 4 over 4, and then this goes from 1 to negative 1. So this is going to be 1 to the power 4 over 4 minus negative 1 to the power 4 over 4, which is 1 over 4 minus 1 over 4, which is equal to 0. So that's it. Now, our positive and negative sign areas cancel out. Now, how do you find the total area if you want? So that's going to be the a to b. We have the absolute value of f of x. This is for case 28. Times dx. So the total area is going to count everything as positive. Everything is going to be positive. So you're going to split the function where it crosses the x-axis. You're going to find the zeros, and then you're going to split the interval, and then you're going to make the negative parts as positive, and then you're going to add your areas. So let's find the total area between f of x is equal to x on the x-axis from negative 2 to 3. So we can see that one of our zeros is equal to 0, x is equal to 0, right? So then we have a is equal to the integral of negative 2 to 0, and we have negative x times dx plus the integral of 0 to 3 x dx. So then this is going to be equal to, we have 0 minus negative, we have negative 2 in the inside, and then we can add our 9 over 2, right? And then we can subtract our 0, and then this becomes 2 plus 9 over 2. So then this is equal to 13 over 2. So it's going to be made positive. For the negative part that's underneath the x-axis, we're going to make it into positive for our total area. So what about our case 29? Case 29 is going to be when we have area between two curves. Area between two curves. So this is not that bad. We just have the area is equal to the integral from a to b, and then we are going to take our top and then subtract our bottom part. So this is all going to be times dx. So the area between the curves is going to be the upper function minus the lower function. So first we have to find the intersections if we're not given them, and then you're going to determine which one is the top and then which one is the bottom, and then you're going to integrate the top minus the bottom. So let's say we want to find the area between two curves of y is equal to 4 minus x squared and y is equal to x plus 2. So let's find the intersections by just setting these two functions equal to each other, because that's when we're going to have the same solutions that satisfy both equations. So you have 4 minus x squared is equal to x plus 2, and then you have x squared plus x minus 2 is equal to 0. So then you can factor this, and you have x plus 2, and then you have x minus 1 is equal to 0. So then x would be equal to negative 2 and 1. So on the interval, we're going to see that this is going to be on top of this function. This is going to be on the bottom on our interval. So for our interval, this is the interval from negative 2 to 1. So basically, we're going to have the area is equal to negative 2 all the way to 1. We have 4 minus x squared, and then we're going to subtract x plus 2, and we have dx of this, right? So then this is going to become negative 2, and then we have 1 over here. We have 2 minus x squared, all times dx, and then we can write this with a definite integral version. So we're going to have 2x minus x squared over 2 minus x to the power of 3 over 3, and then we have a 1 over negative 2 to 1, I mean. So then we're going to do negative 2 in the front first. So if we're at x is equal to, let's just do x is equal to 1. X is equal to 1, we're going to have 2 minus 1/2 minus 1 over 3, which is equal to 7 over 6. And then when x is equal to negative 2, we have negative 4 minus 4 over 2 minus negative 8 over 3. So this is equal to negative 4 minus 2 plus 8 over 3. And this is equal to negative 6 plus 8 over 3, which is negative 10 over 3. So if we subtract these two, we're going to have 7 over 6, which is going to be the x is equal to 1, which is the one that is on top, right? For at least, what I mean by on top is this one on top of this definite integral evaluation thingy. You're going to have 7 over 6 minus the negative 10 over 3. And then that becomes 7 over 6 plus 20 over 6. So this is 27 over 6, and then we can divide these both by 3, and if we do that, we get 9 over 2, aka 4.5, but it's fine. And then let's do our accumulation formula. So all you have is the function of x. You take the integral from a all the way to x, and you have f of t dt. So you have your f prime of x is equal to f of x. So basically you have an integral with a variable with an upper bound. It's going to define our accumulation function. So basically we're going to recognize this inside of our thing, and then we're going to use the fundamental theorem of calculus. So for example, if we have f of x is equal to the lower limit 2, upper limit x, and we have t to the power of 3 plus 4t times dt, we want to find what f prime of t is. We can just say that by the fundamental theorem of calculus. So by the FTC, we can say that f prime of x is equal to x to the power of 3 plus 4x. So that's going to be our answer, because the derivative of an accumulation function is going to be the integrand when you evaluate at the upper bound. So this is going to be when you evaluate at the upper bound. Now, what if we do the fundamental theorem of calculus with the chain rule? So this is for case 31. We have the FTC with the chain rule. So basically you have d over dx integral from a all the way to g of x is going to be f of t times dt. This is going to be f of g of x times g prime of x. So if you have an upper bound that is not x, you have to use the chain rule because it's not x here, so it's going to be difficult to do. Basically, you're going to plug the upper bound into the integrand, and then we're going to multiply the derivative of the upper bound. So let's say we have f of x, or large f of x, is equal to the integral of 1 evaluated to x squared. We're going to have this over t cubed plus 1 all times dt. So if we find f prime of x, this is going to be the square root of x squared times, or to the power of 3 plus 1, all times 2x. So this is all going to be equal to 2x times the root of x to the power of 6 plus 1. So if we have the upper limit of x squared in this case, we had to use the chain rule. So what if we have the fundamental theorem of calculus with a lower bound variable? So we just have d over dx for case 32. This is going to be times g of x times 2a, right? So we have f of t dt is equal to negative f of g of x, and we're going to multiply this by the derivative of g. So a variable with a lower bound is going to create a negative sign. So we're going to plug the lower bound into our integrand, then we're going to multiply by the derivative of the lower bound, and then we're going to add the negative sign. So we have f of x is equal to the integral of x cubed times 5. We have cosine t squared, right, times dt. So then if you find f prime of x, this is equal to negative cosine, and we have x cubed to the power of 2. And we have this times 3x squared. So this is equal to negative 3x squared times cosine of x to the power of 6. So what if we want to find the average value of a function? So this is for case 33 they could ask you about. For the average value of a function, you have f average is equal to 1 over b minus a, from a to b, we have f of x times d of x. So the average value is not going to be the average of the endpoints. It's going to be the integral divided by the interval length. So we have to integrate over our interval that we have. And then we're going to divide by b minus a. And then we're going to simplify. So let's find the average value of the function of x is equal to x squared on the on the interval of 0 to 3. So then we just have f average is equal to 1 over 3 minus 0, evaluated from 0 to 3, and we can have this times x squared and times dx. So we still have 1 over 3 on the outside, so then you're going to write this integral as a definite function version. So basically we just are going to use the power rule on this, giving us plus 1 in the 2, right? So that becomes 3, and then we have division by 3. So then we evaluate this from 0 all the way to 3. So then if we do that, we know that the beginning part is going to, know that 0 is going to cancel out to be 0. So we really only need to do this 3 part. So then we have 3 to the power of 3 is 27. So 1 over 3 is going to be 27, and then we still have division by 3, 27 over 3. So this is going to become 1 over 3 times 9, and then that's just equal to just 3. So what if we have particle motion and displacement? Particle motion, so this deals with the physics aspects of things. We have displacement. This is case 34, and basically we need to know that our displacement, our delta x, is equal to the area underneath the velocity function. So if you have your velocity times time graph here, this is going to be delta x underneath your graph. So you should know that from physics if you've taken it, maybe physics 1 or physics C. Well, we know displacement is going to be a signed change because of the fact we don't see a absolute value sign in the equation. So we're going to integrate velocity, we're going to keep the signs, and then the result is going to be the final position minus the initial position. So let's say we have the function v of t is equal to t squared minus 4t, and we want to find the displacement all the way from time, which is 0 to 5. So let's do this. We have the integral from 0 to 5, and we have the function t squared minus 4t times dt. So then we have t cubed over 3 minus 2t squared from 0 to 5, So then we have 125 divided by 3 minus 50, and then this is equal to 125 divided by 3 minus 150 divided by 3. So then you get negative 25 over 3. How do you find the total distance for particle motion? Particle motion total distance. This is not that bad. So all you have to do for this case is you have to the total distance is going to count all of your particle movement. So you're going to split where the velocity changes sign. So changes sign from positive to negative, because velocity involves direction. And then if you have a change of direction, you're going to be going the positive direction, then you're going to go changing signs. So first you're going to set your velocity time, v of t is equal to 0, then you're going to split the integral, and then you're going to do this at these sign changes, and you're going to integrate the absolute value or flip the negative pieces. So then you add after that. So then let's say we have v of t is equal to t squared minus 4t. And we want to find the total distance that we traveled from time, which is 0 to 5. So we know that v of t, we can factor this, and we would get t times t minus 4. And then using zero product property, we would get t is equal to 0 and t is equal to 4. So that means that when we are looking at 0 to 4, we have a negative velocity, and when we are looking at 4 to 5, we have a positive velocity. So for our displacement, we can take an account for this, and we have our negative integral from 0 to 4 t squared minus 4t. And then this is going to be times dt. And then you're going to just add this to the positive version, which is 4 to 5 t squared minus 4t, because you know if you have a 0, right, every time you cross the x-axis, if you cross the x-axis, this means you're going from negative to positive, back to negative, then to positive. So those velocity points tell us whether we need to, how to split those integrals up, and then how to take those different areas under the curve and then add and subtract them by using that. So it's a pretty, intuitive way if you think about it. Now let's say let's take the antiderivative of this. So then we have for the first part, this is going to give us t cubed over 3 minus 2t squared evaluated from 0 to 4. So this is by using the power rule on t squared. And then let's do this for this later, but let's finish off with this integral first. We have evaluating with 0, that's going to give us nothing, and then we have 60, we know that 4 is going to give us something. We're going to get 64 over 3 minus 32, and then we're going to have, rewriting 32, we can write that as 96 over 3, and we would get 64 minus 3, this would be negative 32 divided by 3. For the second, we would have plus, and then let's see here, we would have at 5 and 4, these would both give us a value. So then when t is equal to 5, t is equal to 4, we would have 125 over 3 minus 50, which is negative 25 over 3. So when you have 64 over 3 minus 32, this would be equal to negative 32 over 3. So if you subtract these two from each other, you have negative 25 over 3 minus negative 32 divided by 3, which is equal to 7 divided by 3. So if you find the total of these two, you can just add them together. We get 32 over 3 plus 7 over 3, which gives us 11, or just gives us 13, I mean. Now, how do we find the position from velocity? Basically, you're going to have the s of b is equal to s of a plus the integral from a to b, v of t times dt. So basically, your new position is going to equal to your initial position, initial, plus your delta x displacement, right? Because the area under the vt is equal to displacement. So you're going to integrate your velocity over the time interval, and you're going to add the initial position. So let's say for a particle, we have a velocity of 3t squared minus 2t. That's what it's modeled by. So we also know that the position of 1 at time is equal to 1 is equal to 5. So then if we have s of 3, this would be s of 1 plus the integral from 1 to 3, and then we have 3t squared minus 2t times dt. So then we would just plug in the fact that that's 5, and then we have t cubed minus t squared, and we evaluate this from 1 to 2. So then when we are looking at time is equal to 3, we know we have 27 minus 9, which is equal to 18, and then when time is equal to 1, you have 1 minus 1 is equal to 0. So then s sub 3 is equal to 5 plus 18, and then you would just get 23. So then integrating velocity, all it did was just change our position a bit. So let's do another example where we have differential equations that are separable. Differential equations that are separable. So 37, this is case 37, you can see on AP Calc BC. This is dy over dx is equal to g of x times h of y. So basically we can separate this, and this would just mean dividing both sides by h of y, and then dividing this by h of y, and then you're just going to take this side and you're going to multiply it by d of x, and this side by d of x. That cancels, and then this cancels out. So then all we have here is 1 over hy times dy, and then this is going to be equal to g of x times d of x. Literally just a little bit of algebra. You're going to move the y's with the y, so we have all y's here, and then we have all of our x's over here. So then we're going to separate the variables, we integrate both of these sides, and then we're going to solve for y if possible. So we have dy over dx is equal to xy. So then we have y of 0 is equal to 3. So then let's just separate this. We get 1 over y times dy is equal to x times dx. So if we integrate this, we get the integral of 1 over y times dy is equal to the integral of x times dx. So then all you have is the natural log of y is equal to x squared over 2 plus c. So then if you exponentiate, you get that y is equal to ce to the power of x squared divided by 2. So then using the fact that y of 0 is equal to 3, then we can just write that 3 is equal to ce to the power of 0. So then if you do so, then we get that c is equal to 3, and you get y is equal to 3e to the power of x squared divided by 2. So what if you have exponential growth and decay? Case 38, exponential growth or exponential decay. So all you need to know is that dy over dx is equal to ky, and y is equal to ce to the power of kt. So basically, if you know that the rate is proportional to the amount, then the solution is going to be exponential. So then we have to recognize the fact that dy over dx is equal to ky. Then we're going to use that y is equal to ce to the power of k over t. Then we're going to plug in initial conditions, and then we're going to solve for our unknowns. So let's say we have a population that satisfies d over p over dt. If you've seen this in AP Bio, you know this is 0.0. 8p, that's the function, right? So we know that we're given that p of 0 initially is equal to 500. That's our initial condition. And we also know that we have to find p of t in this question, is what they're going to ask us for. So then we know that p is equal to CE, and then we have raising that to 0.08 or 0.8 t, and then we'll plug in the fact that p of 0 is equal to 500. So you can set 500 equal to this, and we have CE to the power of 0. So then c is equal to 500, and then p of t is equal to 500, e to the power of 0.08 t. So our growth rate is proportional to the population. Now, what if you had logistic growth? This is the case 39 that you could possibly see. So if you have d over p over dt, this is equal to kp, and we have 1 minus p over L. So logistic growth has a carrying capacity. This is your carrying capacity, and it's going to grow is fastest when we are at p is equal to L over 2. So first we're going to identify the carrying capacity of L, then we're going to find K, and then plug in P if we're asked for the rate. Then we're going to use P is equal to L over 2 for the maximum growth rate. So we'll use that to find it. So we have D over P is equal to over D over T is 0.2 P times 1 minus P over 1,000. So if we have logistic growth, we are going to have our maximum at P is equal to L over 2. So here L is equal to 500. Therefore, P is equal to 500. So we just divided our L by 2. Now, let's do a slope field differential equation interpretation question. So this is going to be when we have dy over dx is equal to fxy. So basically, the slope at any point xy can be found by plugging it into the differential equation. So we're going to plug the point into dy over dx, and then we're going to determine what the slope is. Then we're going to match the field, or we're going to match the slope field or the direction. So let's say dy over dx is equal to x minus y for this, and we want to find the slope at 2, 5. So we're going to have dy over dx is equal to 2 minus 5, which is equal to -3. So the answer is just going to be -3. We just plugged into the equation. So now let's do Euler's method. So this is the case 41 of what we could possibly see. So basically, we know that y new is equal to the y old. And then we're going to take that and we're going to add h times the function times x old. And we have y old. So Euler's method is going to approximate a solution using the tangent line steps. First of all, we're going to identify what our step size is, and then we're going to plug the current point xy into our differential equation. So then let's update the y and then update the x, and then we're going to repeat. So let's say we want to use Euler's method with a step size h is equal to 0.5 to approximate what y is of 1 is, given that we have these two things, dy over dx is equal to x plus y, and also y initial, y with input of 0, right, is equal to 1. So first of all, let's look at when we're from x is equal to 0 to x is equal to 0.5. So for this, we have f of 0, 1. These are our points. So we have 0 plus 1 is equal to 1. So then if we have y is equal to y 0.5, this is approximately 1 plus 0.5 times 1, which is 1.5. So then what if we do x is equal to 0.5 to x is equal to 1? We have f of 0.5, 1.5, and this is equal to 0.5 plus 1.5. So you're just going to add these two, right? You're just adding them because, well, that's not always the case. It's just because that's our differential equation. In this case, we know y of 1. This will be approximately 1.5 plus 0.5 times 2, which is 2.5. So then y1 is equal to 2.5. So yeah, we just have our y new is equal to basically y plus h times the slope. Now let's do an example of where we find. Case 42, we have volume by the Washer method, which is volume is equal to pi, lower limit a, upper integral bound is b, r squared minus small r squared. dx. So basically, we're going to use washers when rotating an area about an axis, and there's also going to be a hole. So we have an axis rotated. We are going to be rotating around this axis, right? And we're going to use these washers. So first of all, you need to know that big R is going to be the outer radius, and then small r is going to be the inner radius. So then you're going to square both, then you're going to integrate this thing. So let's say we want to find the volume found from rotating the region between y is equal to 4 and y is equal to x squared. So we are going to be doing this on the interval of 0 to 2 about the x-axis. So we can draw this out quickly. On our x-axis, we're going to be spinning around here for equation x squared. We have x squared over here. And for y is equal to 4, we are going to go up to 1, 2, 3, 4, height of 4. And we have y is equal to 4 and y is equal to x squared. Now we're going to rotate that from 0 all the way to position 2 next. So our outer radius, we can see, is going to be 4. R is equal to 4, and then our inner is going to be x squared, because these are going to be our limits, right? We don't want anything past beyond there. Let's make this a little smaller. Anything beyond there. So inside of this interval, though, we can see that y is equal to 4 is on top of y is equal to x squared, which is why we're using this. So we can set up our integral here. We have volume is equal to pi times the integral from 0 to 2. We have 4 squared minus x squared times dx. We have pi from 0 to 2. We have 16 minus x to the power of 4 dx. This is going to be pi. We have evaluated 16x minus x to the power of 5 over 5. So basically, when we take the integral, we are going to be adding 1 to this, to the thing that's to the exponent, right? We have x to the power of n plus 1 all over n plus 1 plus c. So then we have, this is a value from 0 to 2. And this is going to be definite, so we don't have to add the plus c here. We're just going to use the power rule on its own. So basically, this is going to be evaluated. We're going to have pi on the outside still, and we have 32 minus 32 over 5. Because when we plug in the 0, we already know that's going to be nothing. So for here, we had everything that was 0. That just canceled out. And this is basically for the x is equal to 2 case. So then we can get a common denominator. We have pi. We have 160 divided by 5 minus 32 divided by 5, giving us 128 pi divided by 5. So we can also do the volume using the disk method. So volume with the disk method is going to look like this. We have v is equal to pi from the lower limit, we have the lower bound being a, and then upper bound being b. We have big R squared dx. So basically, it's going to be the disk method without a hole. So there's no hole in this case. We don't have to subtract anything on the inside. So first we have to identify what the radius is, then we square it, right? And then we multiply by pi, and then we integrate. So let's say we want to rotate y is equal to x squared around on the interval of 0 to 2, right? Around the x-axis. So again, we have x squared, and we're rotating around here. Basically, r is going to be equal to x squared, because that's just our radius here. We have 1 and 2, and we can set this up. We have pi times lower limit 2, upper 2, so lower 0, upper 2. We have x squared times dx, and this is going to be pi 0 to 2, x to the power of 4 dx. This is pi, and we have x to the power of 5 divided by 5, because we just add 1 to 4, and then we divide it by 4 plus 1. And then we have lower being 0, upper 2. So if we plug in, we have pi, and then we have 2 squared over 5. So that's going to give you pi times 4 over 5, aka, 2 to the power of 5. So that's going to be 32. So then we get 32 pi divided by 5. For case 44, we have the volume by cross-section. So volume is equal to lower bound A, upper bound B. We have AX, which is going to be the known cross-sectional area base, and we can integrate this. So for example, let's say we have y is equal to x, and this is one of our bounds. So we have the bounds of y is equal to x, and also y is equal to 0 from the interval of 0 to 3. So we also know that our cross-sectional, or our cross-sections are perpendicular to the x-axis, and they're gonna be squares. Okay, and we want to find our volume. So we can take our area, right? And we can figure this out by knowing that it's going to be a square, right? So we have x squared. And then we can take volume is equal to the integral from 0 to 3, x squared dx. So then if we evaluate this, we can add 1 to 2. So we get x to the power of 3 over 3 from 0 to 3. So then we can plug in 3 to the power of 3 over 3, giving us 27 over 3, aka just 9. We can also find the arc length. So 45, we have arc length, and we get this by L is the integral from a to b, and we have the square root of 1 plus dy over dx, and this is all can be squared, this is dx. So basically we are going to use our arc length, and we use the derivative inside of the square root. So basically we have to find what y prime is, and then we have to square it, and then we have to, so this is our y prime, right? And then we square it, then we plug it into the arc length formula, and we can integrate, or we set up. But here we're gonna just set up. So let's say we have an example of us finding the arc length of y is equal to x squared. So we are looking at this from the interval of 0 to 3. So we know if we differentiate this, right, we get 2x, right, because we just moved the 2 down, and then 2 minus 1 is just equal to 1. So then that becomes 2x to the power of 1. So then you have L. This is going to be evaluated from 0 to 3. So then we have the square root of 1 plus 2x squared times dx. So this is going to be our answer, right? So what about if we have the case of a improper integral, and we can call this an infinite interval? It's a lot of i's, but we have the integral from a to infinity, f of x dx, and this is basically another way of saying the limit as b approaches, because b is our upper bound, right, approaches infinity. We're going to have the integral of a to b f of x dx. So what we have to know is that if you have an infinite bound, that is going to imply you need the limit. So basically you're going to replace infinity equal to b, and then we are going to integrate, and then we take the limit as b approaches to infinity, and then we decide, does it converge or diverge. Basically, let's do this example. It's not that bad. So we have the integral from 1 to infinity, 1 over x squared dx. So you can rewrite this using the limit as b approaches infinity, and we go 1 to b. So this is x to the power of negative 2 times dx. You get from this, you can just say, we have a limit on the outside, right? We have a limit b approaches infinity. So then you can you can write this as the definite integral of negative x to the power of negative 1. Basically, you have to move that negative sign to the front, and then we have to add a 1 here, right? So then after we added 1, right, we got negative 1. So this is going to be from 1 all the way to b. So this can be written as limit as b approaches to infinity. You have, substituting in, we have negative 1 over b minus negative 1, because that's going to work out. And we can write this as limit of b approaches infinity, 1 minus 1 over b, because we have a negative and a negative becomes a positive, right? So basically this is going to, as this is bottom heavy, so this is going to become 0, right? So then you just have the limit of b approaches infinity of 1, and that is just equal to 1, because as we go to 1, which is going to be 1, right? So the limit exists, so the limit exists, therefore we can say that the improper integral converges. Now, what if we have a improper integral with a vertical asymptote? So basically the formula is, if you have from a all the way to b, we have f of x dx is equal to the limit as t approaches c from the left side, because we're going from the negative side, right? So basically this is your positive side, this is your negative side, and if you're approaching from the negative side, you're going to be approaching from the left side. So basically, because you're approaching from the left side, you're actually in reality going to the right side, because you're starting on the left side and you're going to be going to something that is not at the left side. Basically, it's a weird notation, but like it's really essential that you have to know that. Like you should already know that. You have a to b for f of x dx plus the limit of t approaches c from the right side. We have t b, and this is f of x dx. So basically we're going to check if there is a vertical asymptote at x is equal to a constant value c. So we don't know what c is. We want to know if there is a vertical asymptote there. So basically you need to know that if the function is undefined inside or at an endpoint, you're going to use a limit. So let's see here. We have to find the bad point, and then we're going to replace the bad point with a variable, and you're going to take this, you're going to integrate it. You're going to take the limit, and then if any part diverges, then we can say that the whole integral diverges. So let's do this example where we have the integral from 0 to 1 over the square root of x times dx. So our bad point is going to be when we have x is equal to 0, because then you're going to have 1 over the root of 0, and we can't do that because then we're going to have we're going to have division by 0, right? So then we're going to rewrite this as the limit of a approaches 0 from the positive side. We have a to 1, so we have x to the power of negative 1/2, which is the same thing as spreading the square root of, it's like the same thing as 1 over x power of 1/2, and then we just put this in the top using the negative exponent rule, right? So then we can write this is dx. So we have limit as a approaches 0 from the right side, and we have 2x to the power of 1/2, because you can take this and we can move to the front and we just add 1, right? So we have negative 1/2 plus 2 over 2 is equal to 1/2. Now what we can do next is, this is from a to 1. So this is limit of a approaches 0 from the positive side, the right side. And then we have, if we plug in our 2, right, or our 1, we get 2 times 1 to the power of 1/2. And we also get here 2 times the root of a. We can write as instead. So then this is equal to the limit of a approaches 0 from the positive side of 2 minus 2 the root of a, and that's the same thing as 2, so that's just going to be 2. And the reason is because when we're at x is equal to 0, the function is going to be unbounded. So when we rewrite it here, we're going to be limiting the area to something that is finite. Now let's do an example of the integral test for series. Integral test for series. Basically, we know, or the rule is that if f of x is positive, continuous, and decreasing. So all three of these. Then, as we go to infinity, starting at n is equal to 1, a sub n, and this, integral 1 to infinity, f of x dx, either both converge, so this is one case, or both diverge, case 2. Now, basically, we're using these improper integrals to test for convergence for these series. So we're going to match a sub n first. So number 1, you want to match a sub n with f of x. Then we're going to do our checks for conditions. Then you want to evaluate the improper integral. And then we can make our conclusion about whether it converges or diverges. So let's do an example. We want to decide whether this series to infinity, n is equal to 1 over n squared is going to converge using the integral test. So basically we're going to say that f of x is equal to 1 over x squared. So then we can write the integral of 1 to infinity. We have 1 over x squared dx. And then we know that from earlier that this is equal to 1. So if it's equal to 1, and then we can say that we see that since the improper integral, which was this right here, converges, therefore we can say that the series that we were looking at, n is equal to 1 all the way to infinity, 1 over n squared, is going to converge. Because by the integral test, the convergence of the improper integral is going to imply the convergence of the series. So here we have our series. Now, what if we have a Taylor/Maclaurin coefficients from integrating a series? Basically, our formula is just the integral from the series of a sub n, x to the power of n, dx is equal to the series a sub n, x to the power of n plus 1 divided by n plus 1 plus c. So basically, you need to know that you can integrate the power series term by term inside of the interval of convergence. So we're going to start off with the known series, and then you're going to integrate each term, and then finally you can adjust with the constant value if needed. So let's say we have 1 over 1 minus x is equal to 1 plus x squared plus x to the power of 3 ... And we want to find a series for 1 minus natural log of 1 minus x. So since we know that d over dx, negative natural log of 1 minus x, is equal to 1 over 1 minus x, if we integrate this, we have the 1 plus x squared plus x to the power of 3 plus ... dx. This is going to equal x plus x squared, 2 plus x to the power of 3 over 3 plus x to the power of 4 over 4 plus ... plus c. So basically, well, this was because, if you have x to the power of 0 is equal to 1 normally, right? So then if you the other way around. And then basically we just took our 1 plus 1, giving us 2. And then 2 plus 1 giving us 3, 3 plus 1 giving us 4, and then we just divide that all by the coefficient, right? So then here we have negative natural, since we know that negative natural log 1 minus 0 is equal to 0, we can say c is equal to 0. So then we have, in the end, negative natural log of 1 minus x is equal to x plus x squared over 2 plus x to the power of 3 over 3 plus x to the power of 4 over 4 plus dot 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 dot. So now let's do an example where we are going to look at error bound with an alternating series from integration. So our formula is going to be the absolute value of r sub n less than or equal to the first omitted term. So basically, for alternating series approximations, alternate series approximations, the error is going to be the first term you omit, right? It's gonna be the first omitted term. So first you had to first find the alternating series, and then you had to find the first omitted term, and then you're gonna use the absolute value for your error bound. So let's say we want to approximate natural log of 2. So you're gonna use natural log of 2 is equal to 1 minus 1/2 plus 1 over 3 minus 1 over 4 plus 1 over 5 minus whatever comes next through 1 over 5. So then the next omitted term is equal to negative 1 over 6. So that means that your error is going to satisfy our relationship we have here. So that relationship we had up here was absolute value of r sub 5 is less than or equal to 1 over 6. So that is going to be our answer. Now, what if we have a numerical definite integral without a calculator? So we have a to b f of x dx. So some integrals are not meant to be done by hand, and you can kind of just approximate it. So for example, you're going to do it really carefully and then just round it off to 3 decimal places. But you have to show your work. So 0 to 2, e to the power of negative x squared dx. This has no elementary antiderivative, so we can just write this with a calculator, and you're going to round it off to 0.882. Now let's do an example of us finding the Riemann sum. So Riemann sum as a definite integral, we have the limit as n approaches infinity, and we have n I is equal to 1. We have fx1 times delta x. This is going to equal to the integral of a all the way to b f of x dx. And this is from the definition of the Riemann sum, right? We know the Riemann sum is meant to act kind of like an integral, but it's just this other formula that gives us it, right? So it's trying to approximate the area under the curve using a different approach, right? So first of all, we have to find delta x. Delta x is going to be equal to what we have as b minus a over n. So we also have a step as well. So let's do an example. Let's say we have the limit of n approaches infinity. N is equal to I is equal to 1. So then we have 3 2i over n squared plus 1 times 2 over n. And here we have 2 over n. 2 over n is going to be delta x. So delta x is equal to 2 over n. So how can we find our interval length? Well, we know b minus a is equal to 2, so that's going to be our interval length. And we can write xi. This is going to be equal to 2i over n. So we are going to start here. Our start is going to be at 0, and we're going to end at 2. So we have 0 to 2, and we have the function f of x is equal to 3x to the power of 1 plus 1. So here what we did was just, we had 2 minus 0, right? So that was why we had that as our delta x. So we can rewrite the limit as an integral, which is 0 to 2. we have 3x squared plus 1 times dx. So we have sample points from 0 to 2, and then we have a width of 2 over n. Now let's do an example of us using the trapezoidal rule. Basically, t sub n is equal to delta x over 2, and we have y sub 0 plus 2y sub 1 plus 2y sub 2 plus dot 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 plus y plus 2 times y sub n minus 1 plus y sub n. And basically, it's going to approximate our area. It's going to approximate our area using these trapezoids. So first of all, you have to find delta x, and then you have to use your end points once, and then you have to use your interior points once, and then you're going to multiply by the delta x over 2. So let's do an example where we want to approximate 0 to 4 f of x times dx. So if we use a table, we have x and we have f of x. So basically, this is going to give us 0, 1, 2, 3, 4, and we have 2, 5, 6, 4, 3. By the way, this is just the example of the question. And then here we're going to have a delta x that's equal to 1. If we look at the change in our x each time, this is equal length intervals, and we have t sub 4 is equal to 1/2, 2 plus 2 times 5 plus 2 times 6 plus 2 times 4 plus 3. And this is equal to 1/2, and then we have 2 plus 10 plus 12 plus 8 plus 3, and this is going to be 1/2 times 35, which is just 17.5. Now let's do left and right Riemann sums. 54. So left and right Riemann sums. So our formula for the left Riemann sum is you have the summation of f, and you have your left end points, hence the name, delta x. And then r sub n is going to be the summation of your function with input of your right end points, right, times delta x. So the left and the right sums, they're going to estimate your areas using rectangles because it's not going to be exact. So it's going to be doing the best as we can. We have to find our delta x, our widths of our intervals. We either use our left or right endpoints, heights, and then we're going to multiply the height by the width, right? Because, area is equal to base times your height, right? So let's say we have an example where we have table x 0, 2, 5, 6, and then f of x is going to be 3, 7, 4, 10. So our widths, we can see from 0 to 2, this is going to be equal to 2, and then from 2 to 5, this is going to be 3, and then from 5 to 6, this is going to be a width of 1. So then we can see that those are our widths, right? So then if we write our left heights, we can say that f input of 0 is going to give you out 3, right? We know that's going to be 3. And then we know f of 2 is equal to 7. And then also that f of 5 is going to give us a y value of 4. So then if we find L, we're just going to take 3 times 2 plus 7 times 3 plus 4 times 1, because that 3 is going to come from our width of 2. So basically, let's match these up. 2 and 3. 3 times 2. And then 3 is going to come from 7 times 3. And then for 5, f of 5, that's going to come from here, the 4. So we are going to multiply that by 1. And highlight this as well. So then all this is going to be 6 plus 21 plus 4, aka 31. So for our final case, we're going to have integration from a graph. Basically, this is going to be a all the way to b. We have f of x dx. This is going to be the signed area underneath your graph. So basically, you're going to have a geometric area, like a geometric area made up of triangles, rectangles, lines, semicircles, and then you're going to take your graph, right? Graph is going to be something like this, and then you can kind of just eyeball it. And you're going to break it up into shapes. So above the x-axis is obviously positive, below is negative, and you're going to add your signed areas. So let's say that, for example, we have f of x is going to form a triangle above the x-axis. So here is our triangle from x is equal to 0 all the way to 4. So the height is going to be equal to 6. So we can just do area is equal to 1/2 base times height, which is 1/2 4 times 6, which is 12, and we're above the x-axis, so it's going to be positive 12.